So thank you very much for the invitation to speak here. So I want to speak about so what I'm going to speak today about is joint with Colmez and Dospinescu. Okay. Right. And Dospinescu is going to speak after me. So the second talk this morning, and I'll explain a part of the argument, and he'll explain a different part of the argument. Yeah. So what is the argument about? So let's see. So G is GL2QP. Okay, and so P is any prime. So the fact that this P is allowed to be anything is essential, well, kind of is the main point of this talk. And then we prove the following theorem, that if I look at pi, so these are pan-admissible GL, so these are absolutely irreducible, non-ordinary. So I'll come back to these words and look at isomorphisms classes. They're naturally in bijection with rho GQP, GL2L. So this is continuous, absolutely irreducible. And also take isomorphism classes. So what is L? So L is coefficient, so L over QP is some finite extension. So I have some ring of integers, a uniformizer, and then the residue field, maybe it's called little k. And then, so this thing, these are admissible unitary L Banach space representations of G. Okay, so now absolutely irreducible. This means that if I take a Banach space and I extend scalars to a finite extension, but this is irreducible for all L prime over L finite. Okay. So this is what absolutely irreducible means. And then non-ordinary means the following, that pi is not a subquotient of int bg chi continuous for any chi b L prime. Okay, so such representations came up in the second talk yesterday, and subquotients of such representations, we call them ordinary. Okay, so this is the name is motivated by this emittance functor of ordinary parts, which was explained yesterday. So we look at non-ordinary things. So now this is just not, although this will not play such a big role for my talk, but this bijection is just not any bijection. But the way it works, you take this pi, and there is to this pi, you can apply so-called Colmez's Montreal functor, which is kind of somewhat magical, and you get a Galois representation. So this will be explained in more detail in Dospinescu's talk. Yeah, so it's really great giving a first talk. You can claim all sorts of things. It will be explained in the second one. So now, so I guess I did it wrong. So what I should remark is that this was known for p greater equal to 5, but now the proof, this proof is different. This proof is different. Good. Right. So maybe yeah. So before I go into details, for the proof for p greater equal to 5 is kind of a characteristic p proof, and this proof is a characteristic 0 proof. So maybe maybe this will become apparent. So now you see what I want to explain today is a part of the argument, and so let me call this theorem 2, which is the following. So if I have pi such Banach space representation, and I assume that it's absolutely irreducible, and then I choose some theta inside pi. So this is unit ball with respect to some G invariant norm on pi, right? Because this representation is unitary, so I can choose the exists. I mean, by the word unitary means that there exists a G invariant norm which defines a topology on pi. So I just pick one and I look at the unit ball, which gets called capital theta, and then the assertion is either one. When I reduce this modulo the uniformizer, this unit ball in a Banach space representation, I get a smooth representation in characteristic P. So in many assertion, this is isomorphic to pi, irreducible, supersingular. Or 2. So if I reduce this modulo the uniformizer and I semi-simplify, this is contained in the following. So I have NB chi1, chi2, omega inverse. I semi-simplify, NBG chi2 tensor chi1, omega inverse. I semi-simplify. For some chi1, chi2, qp times, so these are smooth characters. Okay, right, so now, so this notation means that I take a Borel, so these are just upper triangular matrices. So this is a character of Borel which sends, well, a matrix A, B, 0, D to chi1 of A and chi2 omega inverse of D. Now this, what is omega? Omega of x is equal to x modulo P for all x in qp times. So this is what I would like to explain, how we kind of prove this. But before doing this, let me also mention how this relates to the next talk. So you see, when I apply this functor v to pi, is essentially the same as applying this functor to theta and then inverting p, okay? But now, so now v of theta is some module, some O module of actually finite rank, and you can read off the rank by applying v to reduction of theta modulo the uniformizer. And now because you know this explicitly, and you know what is v of pi, and what is v of this principal series things, you can conclude the following. If pi so this is absolutely irreducible, then dimension L v of pi is equals to 2, and then equality if and only if pi is non-ordinary. Okay, so a priori, you have no control on the dimension of this space. So a priori could be, say, infinite dimensional, right? But once you get some control on the reduction, you can control, well, on this thing. And once you have this result, you can then apply a different construction due to Colmez, and then developed by Colmez and Ospinescu, which to two-dimensional Galois representation associates, well, a representation of GL2QP, right? Okay, so let's see. So I think I did this in the wrong order. General properties of what? Yeah, so this is either irreducible. This thing, yeah, so I should have said this. This thing, for generic chi and chi2, this thing is irreducible. This principal series is irreducible. It can happen that the whole thing has either 2, 3, or 4.
No, I'm not asking this specific, just the general theory of representations of, like if you start from a Banach, what you call an admissible unitary.
Nothing is known.
Is it a finite length modulo pi?
No, I mean it's not known.
But it is admissible, okay.
Yeah.
It is only known to be admissible.
Well, it's known to be admissible, but you cannot deduce this of that it's finite length.
Okay.
Basically, I mean, if you do representation theory over C, you know that admissible plus finally generated implies finite length. In mod P, you don't have such a statement. In general, in representation theory of p-adic groups modulo P.
But it is finitely generated.
Well, you can, so you know that it's admissible. Let's see, so at least you know that it's locally finite. If you take a, well, wait, so hang on. So I'm getting confused between the particular case I'm dealing with, GL2QP, and the general case. So in general case, it's not known that much, right? It's only known that's admissible.
So for example, the notion of irreducibility, you start from a vector, you know it generates, you start from a non-zero vector, and take the, what do you know about the thing generated by it? Is it?
You know that it's admissible representation and that it's finally generated.
No, but the irreducibility is just algebraic.
So for mod P representation, it's always just algebraic notion. For the Banach space representation, it's a topological notion.
So if you start from a non-zero vector and take the O module generated, the closure of the O module generated by it, is it okay, maybe I can say it.
No, I mean, I think even basically all the troubles, I think, well, maybe, I think even if a group is ZP, then it's already, you kind of see that nothing is that straightforward, right? but okay, so let me proceed with this. Okay, so what do I want to say now? So in fact, it makes me feel better, you know? Let's see. So what I want to explain is how to bound multiplicity of pi in some So I take an irreducible smooth representation over K, so let's say absolutely irreducible, and I want to this is what I want to explain, and theta like in this theorem. So basically, so to prove this theorem, I need to bound multiplicity for each irreducible representation. So this is 1. And 2, I need to be able to say that given that pi occurs as a subquotient, I have to basically have a bound on which other irreducible subquotients can occur. So this last part is done by a theory of blocks, and it works, I mean, pretty much the same way as in representation theory of finite groups. So I don't want to explain this. What I want to explain is this boundedness argument. Okay, so now, so let's see. So I have this smooth representations, G, on O torsion modules. So this is anti-equivalent to a certain category, mod profinite augmented, GO. And this anti-equivalence is done like this. I take some representation and I map it to its Pontryagin dual. So this is Hom O tau L O. And on this thing, I put a compact open topology. Okay, so one can describe exactly what these things are, but for the purpose of the talk, I mean, I just take a discrete thing and I take its Pontryagin dual, right? So I get something compact. So in here, I have this category of locally admissible representations. So this was explained in the second talk yesterday. So this category is due to Emerton, and this just means that for every V in a representation, every vector, if I look at the representation generated by it, this is admissible. So now, so this gives me some category C, okay? By definition, just like whatever I get by taking Pontryagin dual of this thing. So so now one can show, well actually I can, for my purpose, I can actually assume this, but so automatically holds that this pi is admissible. So this is, I guess, due to Berger. That pi is admissible, so this means that if I take Pontryagin dual, so this lies in this category C. So now I look at P, so this is projective envelope of pi V in C, and then I let E to be end CP, the endomorphism ring. Okay, so right. So now, okay. So maybe I shouldn't do this. Maybe do this instead. So now, if I take pi an admissible Banach space, and then I can take some a unit ball as before, G-invariant unit ball, and then I define M of pi. This is Hom C in this category, P theta D, and I invert L. So let's see. So I have this I have this theta. When theta D, I simply take Hom O theta into O. I equip this guy with a weak topology. So this is so-called Shikov dual of theta. And you can show that admissibility of pi implies that this guy actually lies in this category C. So because this is p-adic, I don't have to do this. This has been pointed out by several referees of my papers. Right, so let's see. Okay, so now, yeah, well, okay. So let's see. So what I have is a following proposition, which says the following. So one, that this M pi is a finely generated E1 over P module so this condition of admissibility translates into finely generatedness. Two, now if I look at dimension L of M pi of this module, this is the same thing as dimension K of P theta. I reduce this modulo the uniformizer, so I get something discrete, and I take its Pontryagin dual, and this is the same as Hom. Yeah, sorry. Yeah. Dim K. And you see now this P is a projective hull of this irreducible, of this pi V. So now, this guy, you can actually determine that this is multiplicity of pi in theta modulo semi-simplified. Okay. So you can actually read off a multiplicity if you know the dimension of this module. So this is 1, and then part 3 says if this pi is absolutely irreducible, then part A, this MP is absolutely irreducible, E1 over P module. B and G cont pi. So this M is a functor. So if I have an endomorphism, a G-equivariant endomorphism of a Banach space, this induces an endomorphism of this module. So this induces a map, and the assertion is that this is an isomorphism. Okay. Okay, so now this statement looks kind of a little bit scary, but basically the proof works like this. You imagine that G is a finite group, and then you can just prove this by saying using the book of Serre on representation theory of finite groups. And then you look at this proof, and you realize that exactly the same argument works, except that to deal with issues of duals, continuity, and p-adic function analysis, you have to use a paper of Schneider and Teitelbaum. Oops. Let's see. So, okay. Okay, so now, so this is maybe not so hard. Well, given
what did you write in this category, mod lower G? What is the thing above?
Pardon me?
What did you write? The anti-equivalence goes to mod lower G, and then what was the thing above? Augmented.
Yeah, so this is profinite augmented. So if G was a compact group, a compact p-adic analytic group, so this profinite augmented would be simply compact, linear topological modules over the group algebra. So in my situation, G is not a compact group, so one has to do a little bit of extra things, yeah. But essentially, this is what it is. Okay. So let's see. Right, so now I want to explain one easy corollary of this. This theorem if E is commutative, dimension of L m pi, so pi is absolutely irreducible. Yeah, so I want to explain how to deduce from this proposition. So first of all, I let script E be the image of E1 over P in this end L m of pi. So I may assume that m pi is non-zero. If it is zero, there's nothing to prove. So now I know. So what do I know? So this is commutative.
Is the image of which map?
Well, it's just this is a module over this ring, and I just take a linear endomorphism.
How do you map? Oh, I see. Okay.
Right, so I know that the image is commutative because this ring is commutative by assumption. So now, this implies that this E is contained in end E1 over P of this m pi. Okay, but this is isomorphic by this proposition part 3b b to end G pi op. Now, here I can use Schur's lemma. So the Schur's lemma is not a triviality, but so it is a theorem of Dospinescu and Shren, building on recent work of Ardakov and Wadsley, that the endomorphism ring of this thing is simply L, because pi is absolutely irreducible. Okay, so basically I can conclude that this E is equal to L, but now I know that because pi is absolutely irreducible, implies, again, by this proposition that this m pi absolutely irreducible script E module. And then, because the ring is simply L, this has to be a one-dimensional vector space. So from this, I conclude that dimension L m pi is equal to 1. And I mean, once I conclude this, I can then further conclude pi occurs with multiplicity 1 in theta, right, by using pi 2 over proposition. Yeah? So this kind of is also an easy consequence. Okay, so now I don't want to write this down, but in this proposition I assume that the ring is commutative. So this commutativity can be expressed that for every ordered tuple of elements phi 1 and phi 2, phi 1, phi 2 minus phi 2, phi 1 is equal to 0. I mean, there's no way to argue with that. But now you can generalize this to the following identity. You take, instead of taking 2 elements, you take 2D elements. And then you require, so this is remark, if for all 2D, so now I take 2D elements and I take sign of sigma, and here I compose them. 2D is equal to 0, then one can conclude in the same way, well, okay, so this is, in this thing, I have to use a theorem of Kaplansky. So this would mean, I argue similarly, but now I look at this E, and from this identity I can deduce that E is a ring of polynomial identity. And so then I can argue that the center of this ring is L, and then, I mean, basically Kaplansky's theorem, this assertion follows from Kaplansky's theorem. Okay, so far so good. Okay, so how am I doing? Okay, so that's not too bad. Now, okay, so how to, so I have this abstract proposition, and I know if a ring is commutative, then I can conclude something. So now, how about, so how to prove this commutativity of this ring in some situations? Oops. If I do this, well, that's probably going to be this. Yeah, so how do I prove, how do I get a hand on this case? And the argument is kind of by Zariski density. Okay, so this doesn't mean anything yet, but hopefully right, so now density so now there is a family of representations where I can control this m pi. So these representations have been basically been studied by Berger and Breuil. So now I look at, I give myself, say, I have some finite field extension, and then I have some delta 1, delta 2, qp times to L prime star, some unramified characters. And I guess I want to assume that delta 1 times the norm is not equal to delta 2. So then, to this thing, I can define a smooth, so the usual smooth principal series representation. So this is just smooth principal series representations on L prime vector space. And then additionally, I take V of the form sim A, say L squared tensor det B, an algebraic representation, and I let pi, okay, so I can tensor these things. So now, so this is a locally algebraic representation, and I can consider its universal unitary completion. So this is universal unitary completion. So this universal unitary completion, this means that if I have a G-equivariant map of psi tensor V into some Banach space, then it automatically factors through a continuous map of this Banach space. So now, so far this is just introducing notation, but now, so what is the statement of the theorem? Then pi is admissible G L prime representation and absolutely irreducible, and theorem 2 holds for pi. You unhappy?
I was just saying 10 pi is non-zero.
Yeah. Okay. But of course, this doesn't really play a role in anything. I mean, this makes the statement wrong, but not the doesn't invalidate the statements that come afterwards. Yes.
You have no condition on delta 1 to delta 2 part for this.
Yeah, so this has been pointed out by Laurent that because I don't put any conditions except for this one, the universal unitary completion might be 0. But this doesn't really matter for me. I mean, this universal unitary completion is just done like this. I take some.
Yes, I see that. I mean, what are you asserting then?
So there's been. I have to assume that pi is non-zero. Yeah, sorry. So. Yeah, sorry. Maybe if pi is non-equal to 0, then.
Well, formally it's true for 0 as well.
Yeah, so I wouldn't want to spend too much time with this. Actually, you're right. That's what I was thinking about. That's terrible. Okay, so now I still have 20 minutes, I hope. Okay, so now, so I have this, I know that this theorem 2 holds for pi. So this means that if I choose a unit ball and I reduce the semi-simplify, well, it satisfies kind of, well, one of these things. And so to illustrate the argument, I want to assume from now on, assume pi is supersingular. So this basically means that this pi is not a subquotient of these principal series representations. So then, so this theorem of Berger-Breuil then implies that dimension L, well, M prime of M P is less than or equal to 1. Because pi occurs in the reduction with multiplicity at most 1. Okay? So as a result, we kind of deduce that image E 1 over P in and L prime of M pi. So this is L prime is commutative. Right, so this is a one-dimensional L prime vector space. The action of E 1 over P on this module commutes with the action of L prime. So I get this map, and this is just a field itself, so the image is commutative. Okay, so this is one point. Well, I guess I don't need this anyway. So. Okay. So now, basic idea, try to show that the map E 1 over P into the product. So now I take the product over all such unramified principal series, and which I define over, say, different finite extensions of L, and all their weights V. And to this I have a universal unitary completion, and here I have and L prime MP. And then you try to show that this is injective. So this implies E 1 over P commutative. Okay? Because, well, all of these rings are commutative, and the product is also commutative. So if you can show that this is an injection, you're done. Right, so now, so I should say that motivation is emittance proof of the following fact. So here in a global setting, so Emerton says that proves that classical crystalline points are dense in the big Hecke algebra. So this is as a part of this Fontaine-Mazer paper. So we kind of try and run a similar argument, right? But it gets somehow complicated, a bit more complicated. Maybe with a bit of luck, I'll explain why. Ooh. So let's see. Okay, so now I have 15 minutes. So now, right. So you see, because I assume that pi is supersingular, V of pi is an irreducible two-dimensional mod P representation. So this kind of basic idea, morally, that this injection should hold, morally says that crystalline points are dense in the universal deformation ring of V of pi. Yeah, so this is but now okay, so now I want to sketch. Okay, so this is going to be a sketch. And step one, first of all, we know that P, when I restrict it to K, so K is GL2ZP. So this is projective OK module. Okay, so this is something that one has to prove. But okay, but we know this, so I guess this is so this is maybe due to Emerton and myself. So once you know this, you kind of prove the following. Using this, you prove the following statement. So if for all V, so now you look at algebraic representations of G. So yeah, so these are irreducible algebraic representations of GL2 over L, which I view as representations of GL2 of L. So explicitly, these are sim A L squared tensor that B, A is a natural number and B an integer. Right. So if for all such representations, right. Sorry. I mean, I'm kind of getting excited. So, okay. So have this. I take some phi in this E 1 over P. Okay. Now, if for all V, this phi kills Hom continuous OK P V dual, then this phi is equal to 0. Okay, so how? So this argument essentially already appears in a paper of Emerton. So in this Fontaine-Mesa paper of Emerton. So basically, because you know that this is a projective OK module, you know that this is isomorphic to a product of projective indecomposable OK modules. So then it turns out that it's enough to actually prove the same statement with replacing P with a projective indecomposable OK module. And then it turns out that it's actually enough to prove the same statement with replacing P restricted to K with simply OK, the completed group algebra. And then the statement basically says that polynomial functions are dense in the space of continuous functions. So I mean, yeah. Yeah, so as polynomials are dense in, well, you end up looking at the Banach space KL. So continuous polynomials, or say polynomial functions, are dense in this Banach space. This is what the argument reduces to. So let's see. So yeah. So I guess I can. This is it's not too bad. Right. So now. Should have had this there. Now, as a corollary, of step 1 to step 1, you deduce that this ring injects into a product V of its algebraic representations E 1 over P AV, where this AV is an annihilator of this module, of this HOM OK continuous P V dual. So if I can show that every this ring is commutative, then I can conclude that this is commutative, right? So now in step 2, fix such V G. Right, so now, okay, so now I let this pi p be HOM O P L continuous homomorphisms. So this is a compact O module. So this is a unitary Banach space where I take the supremum norm. Okay. Right. So I should say that in emittance, in analogy to emittance work, this is a local analog of emittance completed cohomology. Okay. But now, if I look at this module, HOM continuous, well, say K P V dual, by Chekhov's duality, so which is so due to Schneider-Teitelbaum, this is the same as HOM K V pi p. Okay. So now, then, by Frobenius reciprocity, this is HOM G, compact induction, KVG pi p. Okay, so now if I let H be the Hecke algebra and the morphism G of this compact induction, KGV, so this is actually, this is a very classical thing. So this is the same thing as compact induction. Since this thing is algebraic, this is the same thing as the trivial representation, and this is isomorphic to T Z plus minus 1. So this is commutative. So this is a nice ring, and it acts on this guy, and it acts on this guy. So now, well, okay, it went away, but we do this step by step. So if I take N, a maximal ideal of this Hecke algebra, and then I look P dual, I look everything that is killed by this maximal ideal N. So then, if you unravel these definitions, this is the same thing as HOM G kappa N, the residue field at N, H compact induction KGV pi p. This thing is a representation of the form I considered before, psi tensor V. where this psi is a ramified principal series with values in this finite extension. And therefore, this is the same thing as Hom G, I guess continuous. So now I can replace this tensor product by universal unitary completion. Okay? And then, if I apply this Shikov duality again, I can deduce that this is the same as psi tensor V with functor M. So at the end, I already know by Berger-Breuil that this thing is one-dimensional over kappa n. So then I can conclude that dimension kappa n of this Hom K continuous P V dual n, that this is 1. Okay. So now, using this, so this is step 3. If I look at endomorphism ring of H, so I take this continuous P V dual, but now I just don't take things by killed just by n, but things killed by some power of n. But this is that I have a surjection on end H E H kappa n. So this is an injective hull of kappa n as an H module in the category of H modules. So now I know what this thing is explicitly. This is isomorphic to H, localized in n, and completed. So this is, I mean, there's a theory called Mutley's duality. Stand up in local cohomology quite a lot. But this is commutative. Okay. So let me see. So I can actually start deleting some of the stuff here. So now I can actually conclude from this thing that if I take end H, Hom continuous, K, pi V dual. So now I take all the elements which when I apply H to it, generate a modular finite length. Okay? So this is what the subindex locally finite means. So this is isomorphic to end H. This is a product over all the maximal ideals of H. I have this Hom cont K P V dual, and here, right? So this is just Chinese remainder theorem. But now, because we have different torsion, this is isomorphic to a product of n or of these. I mean, I don't have sorry, so this should be a direct sum, right, I guess. Yeah. So I don't have, so I don't have a map between individual things, right? So now, so this is the same as Hom continuous, K pi V dual, and infinity is commutative. So this is step 3. in step 4, which just says that Hom k pi v dual locally finite is p-adically dense in Hom k continuous p v dual. So this is compact, and this is a finite dimensional vector space, so I can just take some k invariant norm on this guy, and this makes it into a Banach space. Unfortunately, I don't have enough time to explain the proof of this. But if you believe this, then you can at the end conclude that you have a map E 1 over p divided by the script AV injects into a product N. Well, into this thing. Commutative. And then you conclude that this ring is commutative. So then, right. So then, yeah, it's still there?
Yes, corollary.
Corollary. Well, very good, thank you. So then you can conclude that this thing is commutative. Okay, so now I would only, so this looks quite complicated, right? So what I'd like to say that in emittance setting, because he's in a global situation, he can already stop here. Because he knows that these rings is a product of fields. Okay, so he can stop here, and we have to work harder. Okay, thank you very much.
Thank you for this very energetic talk. Are there questions or remarks?
Yes.
One pi, when E is not commutative.
Yeah. So now I already made remark about this Kaplansky's theorem, right? So now you see. So now, wait. So let's see. So where am I? So now when I use this result of yeah. So in this case, if pi is this Berger-Breuil representation, then I know that m pi can be at most, and let's say it can have a dimension at most 2, and let's imagine it is actually 2. Okay, so then the endomorphism L of m pi. Okay, these are just a matrix ring. And the thing is that every matrix ring satisfies this identity. Okay, so this is, in this case, would be S4, this identity S4. So if I take 4 tuples and I do this, so this is a theorem of maybe Amitsul-Levitsky, right? So, okay, so now, so then I could conclude that the image of my ring E 1 over P in there also satisfies this identity. But then, when I run the same density argument, showing that that this E 1 over P injects into this thing, so then this identity is satisfied for this ring, and I basically proceed then as in remark in this remark on Kaplansky rings, Kaplansky's theorem, rings of polynomial identity.
Other questions? Comments? Yes.
When the ground field is not QP but a finite extension, do you know today that at least the lengths of all these reductions is bounded?
No.
Not?
No, but this is actually a good question. So, because there was a kind of a part of the argument Right, so this is part of the argument. So this proposition that I wrote down on the board, so this holds for any p-adic Lie group. But what I need is a family of representations for which I can control the reduction modulo p and the density. Okay, so now somehow the whole GL2QP theory, in a way, works because this universal unitary completion is irreducible. Yeah? And this kind of corresponds to the fact that there is a unique admissible filtration. And so on one hand, like a part of the argument is very general. The difficulty is finding such a family where you can control reductions. And as far as I know, I mean, apart from some ordinary cases, ordinary Banach space representations, so you can compute the reduction, but apart from this, not much is known.
Any more questions? So if not, let's thank the speaker again.